Okay, isomorphism. So we are going to talk about what this means later by definition. Okay, so before we do that, we want to understand what is one-to-one, onto. So one-to-one. So think about one-to-one function. So we had a one-to-one function, right? So one-to-one function, it's like this. What is the horizontal line test, right? Okay, so parabola, that's not the one-to-one, right? Because there is x value gives the same y value, right? So for instance, f of -2 gives the 4, f of +2 gives the also 4, right? So in order to make one-to-one, we cut positive part or negative part, right? So this is the f of x equal to x squared. X is greater or equal to 0, or f of x equal to x squared. X is less than or equal to 0, right? So for instance, if we have domain here, codomain, oops. Codomain. Oh, come on. I have to yell. Codomain. So 1, 2, send it to AB, right? So basically one element from domain send it to one element to codomain. That's the one-to-one, right? Okay. Now this is also onto. So look, this is onto. This is onto, this is onto. All right. So we have 1, 2, 3. And we have AB. So A send it to A. I mean, 1 send it to A, 2 send it to A, 3 send it to B. Right? That is also onto. Okay. This is not onto. One, 2, 3, A, B, C. So 2 send it to B, 3 send it to B. C does not have anything, right? So that is not onto. And this is not onto. So 1, 2, A, B, C. So 1 send it to A, 2 send it to C, but B does not have that, right? So this is not onto. So can you say that onto means codomain must has by the domain, right? Can you see? So think 1, 2. Think element, each element in codomain was mapped by every element in domain. So basically, we cannot have empty on the codomain. So this is empty, right? Cannot have that. All right, so let us do definition 1-to-1 and on-to. So we are using transformation. Transformation is the function mapping, right? So do I have that? Yeah, so this is a recall from transformation. Okay, this one. Previously. Okay, so during message, I cannot talk right now, so let me talk to you after this, all right? So we have a transformation mapping. So we have this one, right? So means the under closed addition and scalar multiplication. And every matrix transformation is a linear transformation. We did that. Okay, now. Definition. One-to-one transformation. So we have a let V W be vector space with V1, V2 vectors in V, then a linear transformation V send it to W is called one-to-one if whenever V1 is not equal to V2, it follows that T V1 is not T all right, so that is the one-to-one. Now on to definition. By the way, one-to-one, some textbook indicate that this is an injective function. Injective. Definition. Onto transformation. So we have let V W be vector space Then we say that T transformation V send to W be onto if for all W vector W in the W is a vector space, right? So we don't put this notation in the vector space where there exists, not the where exists. There exists. There exists V in V such that T of V equal to W, right? Okay, so this is a surjective. Some book indicate the surjective function for onto. All right, so since we are talking about the solution, right? So one-to-one, we say that only one solution. And most one solution.
Visually what?
All right, so one-to-one, we say that at most one solution. And one-to, we say that at least one solution. So at least one solution means one or more solution, right? Okay. All right. So let us talk about that. We have another equivalent, the definition. So they talk the lemma one-to-one. Okay, so it's equivalent definition of one-to-one. So we have the transformation T of U, I'm sorry, V, they indicate the V equal to 0 vector, then V is the 0, right? So this one we've seen before, right? Okay, now, so we have this one like a null space before. So direct message, I will do that later after lecture, okay? I will remember your request and then I'm gonna do that, okay? So we had a null space of A. So we have a X such that X in Rn and AX equal to 0 vector, right? So we had this one last time. So this one very similar, right? So this one we called kernel. Okay, we are going to talk about more about this definition. Okay, now we have example. Okay, so we have let S is a transformation. P sub 2 send it to M22. So we know this notation, right? We learned this one, polynomial at most degree 2, right? This one we didn't not learn, but looks like a matrix, right? Matrix. In 2 by 2, right? Okay. Now, it's a bilinear transformation. Defined by, so we have a S of ax squared plus bx plus c, which is, so we input polynomial at most degree 2, then we have result 2 by 2 matrix, right? So that is, what kind of matrix we get? It's a special on this example, right? So A plus B, A plus C, B minus C, P plus C, right? This is a special matrix we get on this problem, all right? Okay, now for all ax squared plus bx plus c is in the domain, which is polynomial at most degree 2, and prove that S is 1-to-1, but not onto. Okay. Definition. So we have the linear transformation is called 1-to-1 if whenever the element from domain is not equal to, that follows that T of V is not equal to T of V sub 2, right? So note. That is 1-to-1. Oops. Okay. So let me just denote x sub 1, x squared plus b sub 1 x plus c sub 1 is not equal to a sub 2, x sub 2 plus, no, x sub 2, x squared, b sub 2, x plus c sub 2, right? We say that. Not equal to means distinct, right? They are distinct. Okay. Then we have S of a sub 1, x sub 2 plus b sub 1 x plus c sub 1. And it's not equal to S sub 1, S sub a2 x squared plus b sub 2 x plus c sub 2, right? Since, look, this one gives us, I am following this one. This one, I'm gonna put only sub 1, each one. Oh, okay. One, 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 one. It's not equal to 2, 2, 2, 2, 2, 2, 2, 2, right? Okay. Thus, S is 1-to-1. Okay, now we want to show that S is not onto. All right, so let's make that. We have to have something, for every, oh, you cannot know this notation. For all V is in V and, sorry, W, right? One second. Here will be equal to W. For all W equal to W, and there exists VE in V, so T over V equal to W, right? Okay, but this is not onto, so we are using number. So I am following that codomain element, right? So let's say that the matrix A is in matrix 2x2, and we said the P over X is in the polynomial at most degree 2, right? Okay. But then look, if this is equal, then it's onto, right? So we are going to say that S of P over X is not A, right? So we want to show that, right? Means not onto. This onto. Okay, so A equal to what kind of matrix? So we thank you during message. What kind of A we have to set up? 0, 0, 1, 2. All right, so look. So polynomial, this one, since we have P over X equal to, it's a degree 2, so we can use the AX squared plus BX plus C is in the polynomial at most degree 2. Okay, now let's say we say that equal to A, right? We against with this one. Yeah, actually we want to show them not onto, so we have to make a not equal to, but let's say that's just equal to. What happened, right? Okay, then look, this means 0, 1, 0, 2, which is, where you go? What's the, yeah, that means this. Copy. Same as, yeah. Okay, so that is the corresponding A plus B equal to 0, A plus C equal to 1, B minus 1 equal to 0, P plus C equal to 2, right? So let me write down. Okay, so we are making augmented matrix. Ooh, so nice, direct message. So there will be A, B, C. So A, looking at this one, A, B, 1, 1, C is 0, 1, 1, C is 0 and 0, right? And looking at this one, A is the 1, B is 0, C is the 1. And looking at this one, A is 0, B is the 1, C is the negative 1. And the last one, 0, 1. Ooh, what is the 2? It's a C. So please correct me if I make a mistake. 1, 2. Now, direct message gives us reduce the row echelon form. Wow. So that is 1, 1, 0, 0, 1, 0, 1, 1. Thank you. Direct message. 0, 1, 1, 2. Okay. So looking at the last term, last row, so we have too many numbers, right? So false statement. Say just 1 is not equal to 2, right? So 1 is not equal to 2. So there is no solution. Okay, so no solution means the system is inconsistent. Inconsistent. So we cannot find such a P over X equal to A, right? Yeah. Oh, the RREF is different. Okay, so sorry. The reduce the row echelon form. Let me see. So we have 1, 0, 0, 0. And we have 0, 1. So that's not the one. So 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So still false statement 0 equal to 1, right? So we cannot have it 0 equal to 1. So do that. So therefore, S is not onto, since there is no P over X in the degree polynomial at most to degree 2, right? Such that S of P over X equal to give state. All right? Yeah, sloppy, huh? Okay. So Since we don't have time, let's move on. Isomorphism. That is a title, right? So isomorphism. So we have let V and W be two vector space, and let T transformation, linear transformation. Then T is called isomorphism if the T is 1-to-1 and 2 T is on 2. Yeah, so 1-to-1 on 2. But T must be linear transformation. T is a linear transformation. And T is on 2, 1-to-1, then isomorphism. Okay. All right. They have another statement. Let V and W. Oh. To vector space. And let T, V send it to W. Be linear transformation. Sorry. Then if T is isomorphism, we say that domain, codomain are isomorphic. So V and W are isomorphic. Isomorphism. So we are using transformation T's isomorphism because T is a linear transformation 1-to-1 onto, right? Then the vector space V and W are isomorphic. Okay. Let me see. Let's do one. This problem. The transformation 2x2 matrix and R4, the 4-dimension, right? So be defined by, so we have a transformation T of A, B, C, D, give us 4 entries, right? That means, so 4-dimension, 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 4 entries. Okay, so 4 entries means there are 4 rows, A, B, C, D. And for all A, B, C, D from domain matrix 2x2, show that T is isomorphism. Okay, so just assume I don't want to show this one. T is linear transformation. So because we had every matrix transformation previously, every matrix transformation is a linear transformation. Okay, now we show the T is one-to-one and on-to. So we are using equivalent, the definition. So show that T is one-to-one. Okay, show T of A equal to 0, then A is the 0. For A is a matrix 2 by 2. This is the equivalent definition for one-to-one. Okay, now let A, no, not A, let T of ABCD, right? Equal to A, B, C, D. They defined like that, right? Okay, so we make this is equal to 0. So if we make this is equal to 0, then there must be A equal to 0, B equal to 0, C equal to 0, D equal to 0, right? And A equal to 0, B equal to 0, C equal to 0, D equal to 0. Yeah, so that means A. So this is A, right? Because T of A equal to 0. So I understand your message. Thank you. So this is A, B, C, D, which is 0, 0, 0, 0, because we said A equal to 0, B equal to 0, C equal to 0, D equal to 0, right? So thus T is 1-to-1, right? Because we set up this and then we wanted to show A equal to 0, right? All right, now T is onto. Okay, we said that let X equal to X of 1, X of 2, X of 3, X of 4. This is a 4 entries. So we're using R4. Okay, now, so we are using A equal to X of 1, X of 2, X of 3, X of 4. Then T of A, which is the T of X of 1, X of 2, X of 3, X of 4. There will be X of 1, X of 2, X of 3, X of 4, right? Because they say that here, right? They say that the input matrix 2 by 2, then we get output 4 entries, right? So there will be R4. So that is T over A equal to X. Therefore, T is onto. Thus, T is isomorphism. And the matrix 2 by 2 and not matrix 2 by 2 and R4 are isomorphic. Okay. All right. Any question? Okay, so let us do 9.8 really short. So 9.8, the kernel and image of linear map. So we talked about the kernel earlier, right? We have definition. Kernel and image. And we talked about the image before. So image, we have range, right? We know what is a range. All the y values. Yeah. We talk about that. So codomain, right? In codomain. Codomain. There's a range, and then there is image. So set of all images is range. Yeah. Set of all images is range. So basically, image is part of range then, right? Okay. Now, let V and W be vector space, and there's linear transformation. Then we denote the image of T using, so they're using IM over T. So IM over T is set notation T over V such that V is in V. Okay, now corner we denote this way. So we have V is in V such that T over V equal to 0 vector, right? Okay, can you see the difference? This is codomain, right? This is a domain. All right, there is a difference. Okay. They mentioned that image of T, and kernel of T are subspace of W and V respectively, right? Okay, means that they both have 0, right? They include 0 vector and they satisfied under clause under addition. Addition and clause under scalar multiplication, right? Subspace, right? There's a subspace test we learned. Okay. Let us do just one problem. We are done. All right. Okay. Let us do. Let transformation, linear transformation, P sub 1 R, right? Okay. Look, input. This is the degree polynomial degree at most 1, right? Polynomial at most degree. And this is a real number. Okay, so this is defined by linear transformation defined by T of P of X equal to P of 1. This is defined in that problem, all right? For all P of X is in polynomial at most degree 1. Okay, now find kernel and image of T. Okay, so let's talk about the kernel. Kernel. So we will have kernel is domain, right? So domain, which is polynomial, is in domain, right? Such that what kind of polynomial we need with the transformation, right? So we just follow the definition. Kernel Thank you, direct message. Okay, so we are following that. So we input T over P of X, right? Equal to 0, right? So we are following that. So T of P of X equal to 0 vector. Okay, so this means oops. I used to put them a little bit. Okay. All right. Okay, then we can continue. So there will be P over X is in that log. This one, we get P over 1. So it's a P over 1 equal to 0 vector, which is 0, same thing, 0 polynomial. Then what kind of polynomial we have? The degree 1, thank you, direct message. So we will have AX plus B form, right? Such that, and this AB is in R, and we make equal to 0, so AX plus B equal to 0, right? Okay, now, so let us using that. Since P over 1 equal to 0, this means X equal to 1, right? Okay, good. So we have a P over 1, then we get A1 plus B, which is equal to 0. That is A plus B equal to 0, right? Okay, then, thank you. B must be A, right? Sorry. We are using B equal to negative A, right? Correct. So B equal to, this implies B equal to negative A. Yes. All right. So that is, we can have the AX minus A now. So such that A is in real number. Yes, very good. Okay. So that is a kernel. So we're just following the steps. Yeah. Okay. Now, they talk about the basis here. It's very interesting. Basis. So basis. So we get basis. For kernel of T is X minus 1. That is the basis. Set of X minus 1. Okay. So what is the basis? We had the basis, right? So basis. So polynomial at most degree 1 is a span of X minus 1. And X minus 1 is linearly independent, right? So if we want to show that linearly independent, thank you. Yeah. Yeah, right. One over certain basis, correct. So they have AX minus A equal to and 0. So we have a 0x minus 0 equal to 0. So A must be equal to 0. Yeah. Okay, let us find image over T. Okay, so image over T, which is the codomain, right? So T over V, just following the definition, V is, vector V is in V. Okay, so that will be T over P over X, such that P over X is in domain Okay, so we had experience. What is this? This is P over 1, right? P over 1, such that, and what's a polynomial? So there is ax plus b within the polynomial and most one, right? Okay, then what do you get? We had an experience earlier, right? So this means x equal to 1. So we have a x equal to 1 plus b such that AB is in R. Thank you, the message. So we get A plus B, right? Okay, so A plus B, which is number, right? So there will be R. Any number. Real number, right? Okay, base. This is a really interesting. Base is for image over T. Base is for image of T is 1. Okay, all right. So this means that the image of T is one-dimensional subspace, and it can be entirely spanned by scalar multiple of the vector. Okay, this means what this means? This means 23 times 1, yeah, and 5 times 1, negative 7 times 1, and so on, right? Spanned and linearly independent, we need to show that, and C times 1 equal to 0, that means C equal to 0, linearly independent. Okay. Any question? Looking at him. Hurts? All right. Thank you very much.